Okay, I had rushed through this example towards the end of lecture on Friday, so I want to walk through it one more time because there was a sign error that I made as we were going through the work. So let's just talk about it again. We have a concave mirror that has a radius of curvature of 0.8 meters. So that's the first piece of information we know about this. And then the question asks, how far from the mirror should you put an object? So how far from the mirror should you put an object? So we know we're being asked about calculating for object distance. So how far should we put it so that the image is twice as large and inverted? So let's talk about interpreting this. So we know that the image needs to be twice as large. So you know the magnitude of magnification is going to be 2, but then the fact that it's inverted, that's a negative magnification. So we know m needs to be -2, and again, the minus sign comes from the fact that it's an inverted image, and 2 comes from the fact that it's twice as large. And then the question also asks, is this a real or virtual image? And we'll answer that question. So starting with the radius of curvature to find the focal length. So also what I've listed here is I've listed the magnification formulas in terms of image distance and object distance, and the magnification formula in terms of image height and object height. Magnification being image height over object height, that's the conceptual definition of what magnification means. How much larger is the image compared to the object as it forms? And then I also have the mirror equation here for us to use. So when we start with 1 over d0 plus 1 over di equals 1 over f, we know we're trying to look for d0. We don't know di, but we can maybe use the magnification to figure that out. And we don't know the focal length, but we can use the radius of curvature to figure that out. And if you recall that from class, focal length is the radius of curvature divided by 2. And this is a concave mirror. And recall, for concave mirrors, the focal length, since here's a mirror that's concave, this is the back side of the mirror, the rays that come in parallel here, they all converge in front of the mirror, giving us a positive focal length. So focal length is going to be positive, and in this particular case, it's going to be 0.8 meters divided by 2. And then using this for magnification, we know that minus di over d0 is equal to m. So we can use this to at least write the image distance in terms of the object distance. So we have -2 equals minus di over d0, or do. I multiply both sides by object distance, multiply both sides by object distance, and divide by a -1. And I get 2 times the object distance is equal to the image distance. So we plug it all in. We get 1 over d0 plus 1 over, and I'm going to go ahead and replace image distance with 2 times object distance. So 2 times d0 equals 1 over f, and f is, so 1 over, and 0.8 divided by 2 is 0.4 meters. So I'm going to go ahead and drop the units and just plug in 0.4 since it's in SI units. That should be fine. We'll just keep track of the fact that everything in here will be in SI units. So 1 over d0 plus 1 over 2 d0. We can go ahead and get a common denominator, multiply top and bottom by 2, and combine these terms, and we get that 3 over 2 d0 equals 1 over 2. Depending on how you like to solve an equation like this, you can think about cross-multiplying or multiplying both sides by 2 d0 and dividing by 0.4, whatever you're comfortable with. You should get 3 times 0.4 is equal to 2 times d0, and that gives us that d0 is equal to 3 times 0.4 all divided by 2. And if we simplify all that, that should give us d0 equals 0.6. Yep, so 0.6 meters. So that tells us that if we put this object 0.6 meters in front of the mirror, we should get the desired magnification. At the same time, where does the image form? Well, we know di was just twice d0, which is 1.2 meters. That tells us that we get a image that is a real image at 1.2 meters. And how did I know that this needs to be a real image? Well, anytime we get an image distance that's positive for a mirror, we know that the image is forming in front of the mirror at 1.2 meters. And a positive distance in front of the mirror, that corresponds to a real image. And then finally, we know, well, we were told it's inverted. So we get a real image at 1.2 meters if we put the object 0.6 meters in front of the mirror. So I hope this helps clarify the example in class.